All the physical laws in the universe are delicately balanced and specifically measured for the existence and support of life. The general structure of the universe, the place of our Earth in that universe, our planet's physical features such as air, light, and water all possess properties that are essential to our survival. When we inspect and study at the molecular level, the special creation of the microcosmic world reveals a clear and an even more unique order. At the molecular level, or smaller, such as the atomic level, which is too small to be seen with the naked eye, everything is flawless. The elements that make up our hands, eyes, hair, and lungs, or all of the living things such as plants, animals, trees, and birds that provide food for us, are all specially created building blocks. In his work, The Universe, Plan or Accident, the physicist Robert Clark describes how the building blocks of life were brought into being with a very special and a very superior creation. As if the Creator has given us a kit of prefabricated parts ready-made for the work in hand. One of these special components referred to by Clark is the element called carbon. In many respects, carbon has different properties compared to other elements. These differences make it essential to life. Carbon is the sixth element in the periodic table. Its most important characteristic is that it constitutes the basis of many things on Earth, from our car tires to our computers, from the natural gas we use to cellulose, from the meat we eat to the DNA in our cells. The film you are about to watch provides information about the structure of carbon and allows you to witness a great proof of creation. The element carbon, the basis of all life, is only produced as the result of very special and miraculous reactions in the centers of giant stars. If these miraculous reactions did not take place, there would be no such element as carbon in the universe today, and thus no such concept as life. We describe these reactions as miraculous because they only take place in conditions that are impossible under normal circumstances when they combine together. Let us now examine this phenomenon. The carbon atom comes into being as a result of a two-stage process in the nuclei of giant stars. Two helium atoms first combine together, resulting in an intermediate element with 4 protons and 4 neutrons. This intermediate element is known as beryllium. When a third helium atom is added to beryllium, the result is a carbon atom with 6 protons and 6 neutrons. The beryllium that emerges in the first stage has a different structure to the beryllium found on Earth. The ordinary beryllium in the periodic table has an extra neutron. The beryllium that forms inside red giant stars, on the other hand, is a different version. Chemists call this an isotope. Physicists have long been amazed because this beryllium that forms in red giants is abnormally unstable. It is so unstable that it disintegrates in as little as 1/400th of a second after it is formed. So how is it that this beryllium isotope that vanishes the moment it forms turns into carbon? Does the helium atom that will convert the beryllium isotope into carbon approach and bond to it by chance? Such a thing is, of course, impossible. It is just as, or even more impossible, as a third brick being added on top of two other bricks that have come to be standing on top of one another by chance in as little as a trillionth of a second, before the first two bricks collapse, and in such a way a sound piece of construction emerges. The famous scientist Paul Davies describes this miraculous phenomenon in these words. Carbon nuclei are made by a rather delicate process involving the simultaneous encounter of 3 helium nuclei inside the cores of large stars. Because of the rarity of triple nuclear encounters, the reaction can proceed at a significant rate only at certain well-defined energies, called resonances, where the reaction rate is greatly amplified by quantum effects. One of these resonances is positioned just right to correspond to the sort of energies that helium nuclei have inside large stars. A process known as double resonance takes place in red giants. When 2 helium atoms resonate in union, another resonance causes a third helium atom to join the beryllium atom that emerged in as little as 1/400th of a second, and thus give rise to carbon. This is a phenomenon that cannot possibly take place under normal conditions. George Greenstein describes why this double resonance is such an extraordinary mechanism. There are 3 quite separate structures in this story: helium, beryllium, and carbon, and 2 quite separate resonances. It is hard to see why these nuclei should work together so smoothly. It is like discovering deep and complex resonances between a car, a bicycle, and a truck. Why should such a disparate structure mesh together so perfectly? Upon this our existence, and that of every life form in the universe, depends. Greenstein compares the formation of carbon in the nuclei of giant stars to a phenomenon that could not possibly occur spontaneously, but is reluctant to unequivocally describe this as a miracle of creation due to his belief in materialist dogma. It subsequently emerged that certain other elements, such as oxygen, also form by way of such extraordinary resonances. Fred Hoyle, who first discovered these extraordinary processes, concluded in his book, Galaxies, Nuclei, and Quasars, that this process was far too planned to have come about by coincidence, and despite being a committed materialist, he admitted that the double resonance he discovered was a regulated matter. In another article, he stated the following: if you want to produce carbon and oxygen in roughly equal quantities by stellar nucleosynthesis, these are the 2 levels you would have to fix, and your fixing would have to be just about where these levels are actually found to be. A common-sense interpretation of the fact suggests that a super-intellect has intervened in physics as well as chemistry and biology, and that there are no blind forces worth speaking about in nature. The numbers one calculates from the facts seem to be so overwhelming as to put this conclusion almost beyond a question. So influenced was Hoyle by this miraculous phenomenon that he stressed how other scientists could not ignore this obvious truth. I do not believe that any scientist who examined the evidence would fail to draw the inference that the laws of nuclear physics have been deliberately designed with regard to the consequences they produce inside the stars. It has been estimated that there are currently around 2 million compounds on Earth, with different structures combined in various ways. In the same way that these compounds may be able to form solely by two atoms combining together, they can also emerge from a combination of millions of atoms. The interesting thing, however, is that the fact that every element has its own particular ability to produce compounds. Some elements never combine with another element under any circumstance. Some produce only one or two compounds. Carbon, however, is very different to all of these. It is able, by itself, to establish 1.7 million compounds of different kinds. Bearing in mind that the total number of different compounds in the world is 2 million, we see that all the other elements, excluding carbon, produce the remaining 300,000 compounds. The meaning of this is that carbon is a great marvel of creation. It is also very interesting that there is actually quite a small amount of this vitally important element. Carbon represents only 9 to 10% of living bodies in weight and only 17 parts in 100,000 of the Earth's composition. Despite being present in only small quantities, carbon is still present in every part of our lives, including our own bodies. And there is no other element that can replace it. Carbon's property of being easily able to form compounds with other elements stems from the bonds it establishes. Because of its molecular properties, carbon is able to add atoms of the same type to one another and also to combine atoms of different kinds. Other atoms generally lack this property. They can form bonds with certain atoms, but differentiate between others. Carbon forms very strong covalent bonds with other carbon atoms. Since these bonds are very strong, they allow very large and long molecules to form. The carbohydrates, protein, and nucleic acids in the body are large molecules that result from such carbon bonds. Scientists spent years investigating whether there was any other element that might replace carbon. The element with the nearest properties to those of carbon was silicon. They therefore thought that silicon should be able in some way to build the compounds formed by carbon. However, all their efforts proved to be in vain. Because silicon had no ability to form a large number of compounds with other elements in the way that carbon does. The main reason for this is the strong bonds that carbon forms with its own atoms. The bond between two carbon atoms is very strong, for which reason it permits much longer and highly stable bonds. Although silicon is an element very close to carbon, it is unable to form such powerful bonds with its own atoms. The bond it establishes is weak and unsuited to the formation of long chains. In his book, The Chemical Elements and Their Compounds, the British chemist Neville Sedgwick describes how there is no alternative to carbon. We know enough now to be sure that the idea of a world in which silicon should take the place of carbon as the basis of life is impossible. The Earth is the only known planet to have the necessary conditions for carbon to form and give rise to compounds. For example, the temperature range needed for a carbon compound to be able to form is between -20 and +120 degrees Celsius. Carbon compounds start to freeze at -20 degrees and to fall apart at 120 degrees. We can witness this decay and this falling apart under world conditions. In a forest fire, for instance, the extreme heat entirely alters the structure of tree trunks. Carbon compounds undergo changes, which is the reason that the tree structure is radically altered. The carbon is now lost its original structure. As we have seen, carbon is impaired by temperature changes. If that change were to prevail across the world, life would disappear. This is one of the most important proofs that the Earth is specially created. The temperature range that permits carbon to give rise to organic compounds exists only on Earth. And this temperature range is a highly delicate one. To make a comparison, the temperature on Venus, the next planet to the Earth in the solar system, is around 450 degrees Celsius, and the temperature on Mars, the next planet after the Earth, is -53 degrees Celsius. It is impossible for carbon to give rise to organic compounds in such burning heat and freezing cold. It must also not be forgotten that the temperature in the stars measure millions of degrees, and that the temperature in the vasts of outer space is -273 degrees Celsius, or absolute zero. The fact that only the Earth possesses the specific temperature range necessary to support carbon-based life is a great blessing and a special creation. The important thing is to realize, by seeing these perfections and by knowing Allah's matchless artistry, that one stands in need of Allah and should appreciate His greatness. Allah reveals this fact in the Quran. I seek refuge in Allah from the accursed Satan. Have you thought about what you cultivate? Is it you who make it germinate, or are we the germinator? If we wished, we could have made it broken stubble. You would then be left devoid of crops, distraught. We are ruined. In fact, we are destitute. Have you thought about the water that you drink? Is it you who sent it down from the clouds, or are we the sender? If we wished, we could have made it bitter. So will you not give thanks? Have you thought about the fire that you light? Is it you who make the trees that fuel it grow, or are we the grower? When we examine carbon in detail, we see that not only the formation of this atom, but also its chemical properties have been specially determined. In nature, carbon is found in two separate forms, graphite and diamond. However, the compound it forms produce very different substances. All the very different organic structures, from the cell membrane to tree bark, from the lens of the eye to a deer's antlers, from the white of an egg to snake venom, all these consist of carbon-based compounds. Carbon combines with hydrogen, oxygen, and nitrogen atoms in very different geometrical forms and sequences, thus giving rise to very different substances. Some carbon compounds consist of only a very few atoms, while others contain thousands or even millions. Only carbon atoms can form such long and permanent compounds. In his book, Neville Sidgwick says this about carbon. Carbon is unique among the elements in the number and variety of the compounds which it can form. Over 250,000 have already been isolated and described, but this gives a very imperfect idea of its powers, since it is the basis of all forms of living matter. When carbon combines with other atoms to form organic compounds, the bond established between the atoms is known as a covalent bond. Covalent bonds are formed when two atoms share the same electrons. Electrons revolve in specific orbits around the atomic nucleus. There may be only 2 electrons in the orbit closest to the nucleus. The next orbit may contain 8, and one after that 18, and so on. The noteworthy point is that atoms have a predisposition to make up the number of electrons in their orbits. For example, oxygen with 6 electrons in its second orbit wants to add another 2 electrons, and thus complete the orbit with 8 electrons. No answer can be given to the question of why atoms have such a tendency, but were it not for that predisposition, life forms could obviously never come into being. Covalent bonds are formed thanks to the atoms' desire to complete their orbits. 2 different atoms that want to complete their orbits do so by sharing their electrons. The 2 hydrogen atoms and 1 oxygen atom that constitute water, for instance, build a covalent bond. The oxygen raises the number of electrons in its second orbit by sharing 1 electron with each of the hydrogen atoms. Each of the hydrogen atoms raise the number of electrons in its second orbit to 2 by using 1 of the oxygen electrons. Carbon thus gives rise to very different substances by building such covalent bonds. Methane is one of these substances. The formation of methane comes about by 4 hydrogen atoms building a covalent bond with a carbon atom. Since the atomic number of carbon is 2 less than that of oxygen, the carbon bonds with 4 hydrogen atoms instead of 2. As we said at the beginning, the bonds built by carbon constitute a very wide spectrum. The bonds that carbon establishes with hydrogen alone give rise to the large family known as hydrocarbons. This family includes natural gas, liquid petrol, fuel oil, kerosene, and various machine oils. The hydrocarbons, ethylene and propylene, are the basis of the petrochemical industry. Other hydrocarbons give rise to such compounds as benzene, toluene, and turpentine. The mothballs we put in cupboards to protect our clothes against moths contain another form of hydrocarbon. Hydrocarbons that combine with chlorine or fluorine produce such different substances as anesthetics, fire extinguishers, and the freon used in refrigerators. The covalent bonds that carbon builds with hydrogen and oxygen represent another wide spectrum, including alcohols such as ethanol and propanol, as well as aldehydes, ketones, and fatty acids. Two important substances formed by carbon, hydrogen, and oxygen compounds are the glucose and fructose in the foods we eat that provide us with energy. Cellulose, the constituent of the hard part of trees that represents the raw material for paper, beeswax, vinegar, and formic acid, again form as the result of the covalent bonds that carbon constructs with hydrogen and oxygen. When carbon builds bonds with hydrogen, oxygen, and nitrogen atoms, very important compounds once again result. The most important of these are amino acids, which form proteins, our body's building blocks. The nucleotides that make up DNA are also molecules made up of carbon, hydrogen, oxygen, and nitrogen. In short, the covalent bonds constructed by the carbon atom are among the most essential preconditions necessary for life. If carbon were unable to build covalent bonds with oxygen, nitrogen, and hydrogen, then life could not exist. What enables carbon to form these bonds stems from a characteristic chemists refer to as metastability. The well-known biochemist John Burdon Sanderson Haldane describes this feature as follows. A metastable molecule means one that can liberate free energy by a transformation, but is stable enough to last a long time unless it is activated by heat, radiation, or union with a catalyst. This technical definition means that the carbon atom has a very unique structure, thanks to which carbon is easily able to form covalent bonds under normal conditions. However, there's one very interesting point here. Carbon's metastability, which is essential for life, only applies within a very narrow temperature range. Above 100 degrees Celsius, carbon compounds become highly unstable. We all observe this in our daily lives. An example of this is when we cook a piece of meat. Cooking it is actually changing the structure of the carbon compounds. One important point needs to be emphasized. The meat that is being cooked now becomes entirely dead. In other words, it assumes a completely different structure to that in a living organism. Most carbon compounds decay at above 100 degrees Celsius. Many vitamins break down at once. Sugars undergo structural change in the same way and lose their nutritional value. At a slightly higher temperature, 150 degrees Celsius, for instance, carbon compounds start to burn. In other words, the upper limit of the temperature range for carbon compounds to establish covalent bonds and maintain these in a stable manner does not exceed 100 degrees Celsius. At a temperature lower than 0 degrees Celsius, however, organic biochemistry becomes impossible, yet other compounds are different. Most inorganic substances are not affected in this way by temperature changes. In order to see this, you can place some metal, glass, or stone in a frying pan next to a piece of meat, and then heat them up. You'll see that as the temperature rises, the structure of the meat changes, it darkens, and eventually burns. Yet nothing happens to the metal, glass, or stone, not even if you raise the temperature by hundreds of degrees. Close inspection shows that the temperature needed by carbon compounds in order to build and maintain covalent bonds is exactly the range that exists on Earth. Yet, as we have already said, the temperature in the universe as a whole vary from the fierce heat of millions of degrees inside the hottest stars to absolutely zero, or minus 273 degrees. Yet the Earth created for human beings possesses just the temperature range required by carbon compounds, the building blocks of life. One more striking aspect of all this is that the temperature range is also one which water assumes a liquid form. As we saw earlier, water, one of the essential preconditions for life, needs exactly the same temperature range as carbon compounds. Yet there is no natural law that makes such a harmony necessary. This is an indication that the properties of water, carbon, and the earth were created to be compatible with one another. The flawless nature of Allah's creation is revealed in the Quran. He who created the 7 heavens in layers, you will not find any flaw in the creation of the All-Merciful. Look again. Do you see any gaps? Then look again and again. Your sight will return to you dazzled and exhausted. Covalent bonds are not the only bonds that keep the atoms in the living body together. There is a second class of bonds. These bonds of different kinds are collectively known as weak bonds. Proteins, basic building blocks, owe their complex three-dimensional shapes to weak bonds. In order to clarify this, we now need to touch on the structure of proteins. Proteins are generally referred to as amino acid chains. This is an accurate definition, though an inadequate one because the term amino acid chain calls to mind a two-dimensional series, like pearls strung out one after the other on a necklace. However, the amino acids that constitute proteins have a three-dimensional shape, like the leaves on different branches of a tree. Covalent bonds keep the atoms that comprise amino acids together. Weak bonds, on the other hand, combine amino acids together in the requisite three-dimensional form. Were it not for the weak bonds, proteins could not exist, and there could be no life in the absence of proteins. The noteworthy aspect of this is that the temperature range required by weak bonds is, as with covalent bonds, exactly the temperature range that exists on Earth. Yet weak bonds and covalent bonds have completely different structures. And there is no natural reason why they should both require the same temperature. Nonetheless, both classes of bonds are established at the same temperature. If covalent bonds were stable at a different temperature than weak bonds, then protein building would be impossible. All of this information about the extraordinary properties of the carbon atom shows that there is enormous harmony between this atom and other atoms and compounds that are the essential building blocks of life, such as water. There is also harmony between the stability of this atom to form bonds and the temperature of our planet. Our planet provides a home for all these elements and compounds. Michael Denton emphasizes this fact in his book, Nature's Destiny. Out of the enormous range of temperatures in the cosmos, there is only one tiny temperature band, in which we have 1. Liquid water, 2. A great plenitude of metastable organic compounds, and 3. Weak bonds for stabilizing the 3D forms of complex molecules. As we have already seen, this narrow temperature range exists solely on Earth among all the known heavenly bodies. What is more, carbon and water, 2 of the main building blocks of life, are found in large amounts on the Earth. All this goes to show that the carbon atom and its extraordinary properties were specially created for life, and that the planet Earth was specially created for carbon-based life. What does a glittering diamond have in common with a drill bit? An uncut, raw diamond is the hardest of all minerals and all substances. For that reason, crystal diamond is used to cut, pierce, and plane substances of all kinds. Hardness is the resistance that minerals display to scratching due to external forces. Minerals can easily be defined according to their hardness. A mineral's relative hardness can be determined by scratching it with another. Scientists who established a scoring system in order to determine the hardness of all minerals awarded the diamond 10 points out of 10. So what is it that makes the diamond so hard? It is noteworthy that the brittle and soft graphite used in lead pencils consists of the same atoms as diamond. Like diamond, graphite is made up of carbon atoms. Yet one is very soft and the other exceptionally hard. One is like a piece of black coal, whereas the other can have a glittering surface. One is present in abundant quantities in nature, where the other is a rarity. For all these reasons, diamond is of course incomparably more valuable than graphite. So how is it that the carbon atom is able to assume both of these totally different forms? The crystal structure of the diamond is the most perfect example in the whole crystal world. The carbon atoms in a diamond crystal have the ideal geometrical form to endow the diamond with its great hardness. Although graphite also consists of carbon, its atoms are not laid out in the same way as in the diamond. This state of affairs is known to scientists as allotropy. Allotropy is the existence of different physical forms of a chemical element by its atoms being arranged in different ways. Each of these different forms is known as an allotrope. For example, oxygen and ozone are allotropes of the oxygen atom. Diamond, graphite, and amorphous carbon are all allotropes of carbon. Some of the physical features of diamond and graphite are as follows. As we can see, there are enormous differences between these two substances, based solely upon the difference in the arrangement of their atoms. All of the properties that make the diamond valuable depend on conditions emerging during its formation. The extraordinary conditions necessary for the diamond to form are extreme heat and extreme pressure. The diamond is born in the depths of the Earth's crust. Parts of this that contain melted diamond may erupt onto the surface and freeze, although this is a very rare phenomenon. That explains why the number of diamond seams on Earth is very low, there being only a few rich deposits. The structure of natural diamond and the way it forms have served as a guide for scientists, thanks to which artificial diamonds can now be manufactured. In some experiments, graphite kept at a pressure of 100,000 atmospheres and at a temperature of 3,000 degrees Celsius was converted into diamond. However, synthetic diamonds are not as valuable as natural ones. Because of their hard structures, such artificial diamonds are used as a kind of abrasive in industry. As Sidgwick the chemist has said, the carbon atom, which contains only 6 protons, 6 neutrons, and 6 electrons, is a fully fledged miracle. The difference in the way the atoms are arranged gives birth to such different outcomes. The way that these outcomes are so beneficial for man is sufficient for us to see that all these are a blessing from Allah. Therefore, it is impossible for any of the properties of the carbon atom, which are so essential for life, to have come about by coincidence. Allah created the carbon atom with all of its different characteristics, just as He did everything else. What is in the heavens and in the earth belongs to Allah. Allah encompasses all things.